organizers for inviting me to come give a talk about one of my favorite topics, thermal properties of cometary nuclei. So what I thought I would do is sort of take kind of an observational approach toward giving a little bit of a summary of what we think we know about thermal properties. So what I thought I would do is start off by talking about what we think we know from looking at a few objects in really extreme detail, what we think we know from looking at many, many objects in not nearly as much detail, but looking at many objects. So to sort of give an idea of what we, like I said, what we think we know about about cometary nuclei from both approaches. I also wanted to talk about some observational limitations, and then I'll finish with some open questions that maybe we'll talk about today when we talk about icy bodies. So when we talk about looking at a few objects in really heavy detail, that basically comes down to looking at comets that have been visited by spacecraft. And here's a list of ones that have been visited. We're going to hear a lot of stuff about 67P today. So I will leave that discussion of all that to the experts, because we'll hear about it later. So I'm going to focus on some of the other objects. Here is a little montage of all the objects that have been visited by spacecraft with the spacecraft photo. And there's a little bit of, you can get some thermal information about thermal properties from all these ones that have been flown by. Like I said, you get a lot of data from a spacecraft flyby. So it's a very useful way to get detailed information about a few objects. So what I thought I would do is basically just focus on a little bit, because just sort of, again, just to sort of summarize things. So there has been some results on the thermal properties of Borelli up here. There's a paper by Soderblom et al. And by Jianyang Li et al. A few years ago, talking about trying to understand what the temperature of the surface of Borelli is at different points in the surface. There's also been a lot of work done. I think the most work on cometary nuclei in terms of the spacecraft flybys, most of the work's been done on Tempel 1 and on Hartley 2, and that's what I wanted to focus on. That will be, well, okay, yeah. I mentioned Jianyang Li has worked on, et al. Have worked on Borelli, and then Olivier Groussin has a paper from just a couple of years ago about Tempel 1 and Hartley 2. So I thought I would go into some of the detail about that, because like I said, that seems to be where most of the effort has gone. So this is a picture from their paper. It shows each column, well, okay, so the first three columns are 103P, so Hartley 2. The last column is 9P, Tempel 1. The first row is a visible wavelength reference image. This row shows, a little bit cut off, but this is reflected sunlight in the near IR, and this is thermal emission in the near IR. So they have near IR spectrometer on Tempel 1, on the Deep Impact. You can get spectral maps of the comets that Deep Impact flew by, and like I said, this is reflected sunlight, this is thermal emission, and you can see there's differences, right? These are two inbound images when Deep Impact was inbound toward Hartley 2. This is an outbound image. What you're looking at over here, this is the morning side of Hartley 2, and this is the afternoon side of Hartley 2, and this is actually, I think, the morning side of Tempel 1 also. So Groussin et al. Did a very detailed analysis of some of these images. They came up with several things that I thought were pretty interesting. So this is a scatter plot showing the temperature that they measured at different points on the nucleus. This is for 103P, so Hartley 2. The temperature at different points on the nucleus as a function of incident angle of sunlight, right? So 0 degrees, that would be the sun is overhead in terms of local sky, and 80 degrees means the sun is really low, close to the local horizon, right? So the funny thing, or the interesting thing, I guess, is that you see out of this, that there's almost no dependence on incidence angle and what the temperature is on the surface of Hartley 2, right? And that goes for both the inbound image that they studied and the outbound image that they studied, right? So there's, you know, you'd expect there to be a lot more temperature structure given the incidence angles, because that's sort of one of those fundamental things. For reference, this is, if you had just had a Needham model with, say, 8 equals 1, no thermal inertia, right? You just sort of expect a temperature structure like that, right? And you see it's totally different. It's much hotter, even at very oblique angles. Even when the sun is just above the horizon, the surface temperature of Hartley 2 is really hot. What's also interesting is the fact that at these really low incidence angles, it doesn't quite get as hot as you'd expect, right? So it's a little bit cooler here, and it's a little bit hotter here. Actually, quite a lot hotter here. And they did the same analysis on 9P on Tempel 1, and they get about the same thing. again, scatter plot of the temperature as a function of incidence angle. So the temperature heats up really fast after the sun rises from a local position. And in this case, the positions at low incidence angle weren't cooler than expected, but still, there's not a lot of dependence on incidence angle in these temperatures, right? So, so the conclusion Grusin et al. Put in their paper is that, okay, there's a lot of roughness on the surface, and that there must be a lot of sub-resolution element structure topography on the comets that sort of puts some of the facet, if you will, sort of more into direct sunlight, even right off the bat, right after the sun rises from a local position, right? So that's not anything that's necessarily unexpected, I guess, especially given all the stuff we heard yesterday about the asteroids, right? But this is pretty much, this is the, for 9P and 103P, that's the only commentary, the only comets where we've actually been able to get data enough to actually show that, yes, okay, this, the roughness of the surface actually comes out in the data, and everything gets really hot really fast. They tried, Grusin et al. Tried to use, so they have a thermal model in the paper. It accounts for conduction and all that. I mean, it's a thermophysical model. They have the shape, obviously, from the spacecraft flyby. So they attempted to model the temperature map using the usual things, right? So this is the result from their paper. So the first column is the temperature map in the data. So this is, so you can see the scale bar here for what the temperatures are. So this is, again, this is the morning side. This is the afternoon side. These are Hartley 2. This is Temple 1. And the knob they had to turn on their thermal model was the thermal inertia knob, right? So capital gamma. And you can see that it didn't matter what gamma they chose, right? They never were able to reproduce the temperature map, right? So it was, so there is the simple model, the simple thermal model wasn't actually able to reproduce the data. And what was really dramatic to me was actually even Temple 1, right? Temple 1, it turned out, not only does it not match, right? It does a really awful job of matching, right? There's giant chunks of the nucleus here that are way colder in the thermal model than it turns out, right? There's a bunch of positions on Temple 1 that were much hotter than you'd expect. So the simple thermal model where you just turn the thermal inertia knob didn't actually work out. So they, so this was, the paper talks about how we actually have to, or they have to worry about the next level of complexity in the thermal model to actually explain what's going on the surface, to explain what the temperature of the nuclei, the temperatures they're seeing on both nuclei, right? And again, that's not necessarily anything unexpected because of what we like I said, what we heard yesterday about all the asteroids, right? We know that there's got to be some level of complexity to understand what the thermal data are talking about, but these are the only nuclei for which we have that level of data. They were able to get an upper limit on the thermal inertia. They were able to modify their thermal model. This is what they put in the paper. They were able to modify the thermal model a little bit and try to constrain the upper limit on the thermal inertia. I mean, obviously they couldn't do it this way, but they still made some arguments for putting upper limits. What was interesting is that the upper limit they got for I think it was Hartley 2 is an the upper limit they put in the paper is 250 in MKS units, right? So that's much higher than sort of the number, at least I think most of us have rattling around in our head about what we think a thermal inertia of a cometary nucleus is, right? It's probably not 250, but that was what they were able to pull out. I guess it was considered a conservative upper limit, right? So 250 for Hartley 2, and the number that I think they got for Temple 1 was 45 in MKS units, in those crazy MKS units. So this is, like I said, this is you get a lot of data on a few objects in the population of comets, and you get a ton of data and you try to understand it. And it's the usual thing where you have so much data, right? You have too much data because then it becomes hard. The more data you have, the harder it is to actually explain what's going on, right? But you can actually understand a lot of detail about the nuclei if you have this level of data. The other approach, as I mentioned at the beginning, is to sort of go the other way and just not take as much detailed data, but try to look at a lot of objects. So this is something that I started to do when I was doing my PhD dissertation in the 90s. Basically, we'd use ground-based telescopes to try to go one at a time to get a bunch of nuclei. And the goal was eventually to build up a giant database of thermal properties of cometary nuclei. But like I said, you had to do it one at a time. It wasn't easy because it's not always the telescopes you have access to. It's not always not always a lot of targets available at a given time, shall we say, right? So it took a long time to build up a list of nuclei that you actually detected from ground-based telescopes. And I've listed some of the ones here. I'm sorry if I've left off your favorite comet. I try to remember as many as possible, but you know, so Hyakutake, Hale Bopp, Enki, Iran-Rigaud, also some of the classic ones, right? These are the ones where the nucleus properties were done way back in the 80s, Iran-Rigaud, Temple 2, Newman 1. So you can do this from the ground. With Spitzer, we were able to, it became a lot easier to study nuclei because of the sensitivity. So a lot of us started getting space-based data with Spitzer Space Telescope. And you could do shots again. You could do one at a time and slowly build up a database. And usually the context is that, oh, there's a comet that's maybe coming close by, or there's a comet that's intrinsically interesting for some other reason. Let's go observe it, right? So that's what a lot of these were. Right, AP Tuttle had a very good apparition a few years ago. SW3, the comet that broke apart. So it was a very nice apparition for that one. Enki is always interesting. Virtanen was used to be a spacecraft target. These are main belt comets, 133P and 176P, right? So these are all comets that were interesting for some other reason. And it's like, why don't we go observe it with Spitzer? That'd be great, right? So this is another way to sort of try to understand something about the thermal properties of the ensemble. One thing we wanted to do with Spitzer was also take a not necessarily an unbiased approach, but maybe a less biased approach by trying to look at a bunch of comets that weren't special for some reason. So this was the next step. This is the project that we were involved in, is trying to do a survey of cometary nuclei with Spitzer, but trying to just pick, in fact, we wanted to pick a bunch of comets that were boring, right, or run-of-the-mill, right? We didn't want to pick the comets that were exciting for some other reason. We wanted to pick a bunch of comets that no one would normally look at otherwise, just because we wanted to figure out what was typical in the ensemble, right? So that we started this survey of ensemble physical properties of cometary nuclei, which we affectionately call SEPCON, with Spitzer. And we decided we wanted to pick a large fraction of the known comet population at the time. The data we took for this was in 2006 and 2007. So the number of comets is now, number of known comets is larger than back then. But we picked 100, we wanted to do 100 Jupiter family comets with Spitzer in a, like I said, in a relatively unbiased way, maybe less biased way. We're looking at a bunch of typical boring run-of-the-mill comets, right? So we tried to observe 100 of them with Spitzer. We actually detected 89. So we felt like this was a nice result. A little bit more about the survey. We only looked at JFCs, so Jupiter family comets, just to keep the sample reasonable. We didn't look at Halley types, and we didn't look at long period comets. We tried to look at all these objects when they were far from the sun, so between 4 and 5 AU, heliocentric distance, right, because we want to minimize coma. So we're trying to look at them when they were far away and hopefully less active. This was the largest sample of thermal detection until WISE and NEOWISE. This was the largest sample of detections from nuclei. So, like I said, we wanted to get a bunch of objects and sort of do a statistically significant sample. And if you want to read about the details, it's in 2 papers. One that was led by me and one that was led by Mike Kelly. But I'll show you some of the highlights from this. So here's a sample of some of the detections we got with the IRS peak-up imaging camera on Spitzer. This is back when Spitzer was still in cryo phase. So these are 16 comets. Each comet on the left panel is a 16 micron image. On the right panel is a 22 micron image. And you can see that a lot of them were indeed point sources, right? So 6P Dores was a point source, 7P Pons-Winicky was a point source. But you do see a lot of them, a lot of comets that even at, like I said, at 4 or 5 AU, they still have some extended emission. So like Coma Solar, 32P, has a lot of dust around it. 37P4, 22P COF, right? There's a little bit of dust around some of these. In fact, it turned out, even though we were looking almost at aphelion for most of these JFCs, like a third of them had extended emission from dust. There were some we also didn't detect, so you can see like 54P DeVico Swift, it was an limit. So we have 2 wavelengths from about 50, it was 57 objects. We have 2 wavelengths. We get nucleus photometry. Some of them were active, but we extracted the nucleus using photometric extraction techniques. We got nucleus photometry at 2 wavelengths. What do you do when you have that kind of data? You fit the NEATM, right? The standard thing. So you get nuclear effective radius and beaming parameter. Oh, shoot, that wasn't Eta, really. You get the effective radius and you get the beaming parameter out of the photometry. Oh, and that was a lambda too. Oh, sorry about that. my fonts. Yeah, so we were able to get beaming parameters for 57 nuclei, right? So up until then, up until this time, it would have been, you know, the number of beaming parameters known for nuclei was much smaller. So getting 57 beaming parameters for nuclei was a significant improvement in the total number. So this is a scatter plot of all the beaming parameters. So the y-axis is beaming parameter. It's just comet by comet here, right? And there's 57 of them. The open symbols are comets for which there was a little bit of extended emission and we had to extract a nucleus. The closed symbols are comets where it was just a point source. So we didn't have to extract it. They were already bare, right? And so some of these have really big error bars, and you can see that, you know, I'm not going to claim that some nuclei actually have beaming parameters that are super high here, right? We've got, you know, the error bars are what they are, and we thought, okay, is there a better way to actually show what's going on in the distribution of beaming parameters for these 57 objects? So maybe the better way to show this is like this. So this is the same data, except instead of the y-axis being beaming parameter, the y-axis is offset from the mean in terms of number of error, in terms of number of sigma, in terms of the error bars, right? And so everything sort of hangs around the mean pretty well when you account for the error bars, right? So when if a comet has a beaming parameter that's way off the mean, but the error bars are big, right? That's sort of reflected. It's a little bit easier to understand that it's still okay as a beaming parameter measurement, right? So if you were to make a histogram out of this, it actually turns out really well. You get this nice Gaussian. The distribution is pretty good, right? They all hang around to mean. For 55 of the 57 objects we measured, the beaming parameter actually hangs around the mean and it, you know, if you start off with the idea that the nuclei have about the same beaming parameter, right? The data are pretty much consistent with that. There's two outliers, right? So there's 89P and there's 2005 JQ5, which I think now is 300P, right? But there's two objects that are outliers. They're more than 3 sigma away, and with this number of objects, you would not expect any numbers to be 3 sigma away. So those are the two outliers. But 55 of the 57 are statistically consistent with having a single value. And what's also cool about that is that the value turns out to be 1, right? So the dreaded fudge factor of the beaming parameter, right? Happily, it turns out that 1 is a pretty good value anyway, right? So we were actually kind of pleased with how that turned out. It was like, oh, the beaming parameter, you know, because this is the kind of thing you take sparse data, sparse thermal data on a nucleus. You don't actually know ahead of time what the beaming parameter is going to be, and so that might mess up, you know, bias what answer you finally get out for the radius and for the albedo and whatnot, right? But it turns out that if you assume a value of 1.03, you're doing pretty good, and you don't have to worry about it, right? The fact that it's 1.03 means that there's not so much, the fudge factor is not as much of a fudge factor as you might think. So that was kind of nice. You can also sort of work that number a little bit more and try to understand something about the thermal inertia. So this is the Spencer thermophysical parameter that was mentioned yesterday. If eta is approximately 1, and you say like, okay, that means that probably the nuclei really are slow rotators, right? So if they're slow rotators, that means the thermophysical parameter is 1 or less, and probably much less than 1. If you throw in typical numbers for the other stuff in here, so this is the rotational frequency, subsolar temperature, emissivity, and you say like this can be no bigger than 1, what do you get for the gamma, for the thermal inertia, right? So you put that in, you put the numbers in, and you get something like a limit of about 20 in the MKS units, which is again kind of a nice result. So again, if you start off with the notion that eta equals 1 means that they're slow rotators, then the limit on the thermal inertia is about 20 in MKS units. Okay, I use the kind of the classic astronomy weasel symbol of less than or approximately of the order of, right? So I'm not saying that all the nuclei are less than 20, right? But 20 is a kind of a good number that sort of describes the ensemble. At least that's the claim. What really helps is that we were looking at these objects so far away, right? So the critical number in here is the subsolar temperature, right? So if you can drop that has to drive down the thermal inertia a lot, because if you're cold, it's much easier to have thermal emission, okay, or the thermal memory, right? But we found that there was still no thermal memory even when they're out at 4 AU, when the subsolar temperature would be something like 190 Kelvin, right? So that means the thermal inertia has to be super low. So like I said, this is an example of going the shallow amount of data, but doing lots and lots of objects. This is the kind of thing you can do. Like I said, the next step in this is WISE and NEOWISE, because they have actually detected way more comets than we did with this pointed Spitzer program. WISE and NEOWISE just did all sky survey, and they found lots and lots of objects, lots and lots of nuclei. This is a montage of some of the comets that were discovered by WISE. So this is 20 of them. There's a few more, but this is a nice rectangle shape, so it fits on the slide very nicely, right? So so these are the 20. There's a paper that has just been submitted by Gerbs-Bauer to the APJ describing some of the properties of the nuclei that was discovered by WISE. And you can do the same thing. You have multi-band photometry with WISE. Some of them are active, but you can extract the nucleus. And you get the nucleus photometry, you convert it to physical properties, and things look like they're consistent with about 8 = 1 too. So, yeah, 8 = 1 also. And this is just 20 of them, but there are dozens and dozens more. Yeah, there's dozens of more in the WISE database. People are working on that now to try and understand the properties of everything in the WISE database. Like there's going to wind up being 150 objects or something like that. And they're also not just JFCs, but there's Halley types and long period comets in the WISE database also. Okay, so observation limitations. I mentioned that we do this photometric extraction thing when the image of the comet looks like it has extended emission. How do you know that a point source is just a nucleus? That is, admittedly, we talked about this in the paper, but this is admittedly one of the fundamental assumptions, is that when you do that technique, you pull out a point source from the image of the comet, and that point source is identical to the nucleus, right? So here's some examples from SEPCONs, 173p, 101p, and 69p, right? So here was the actual image, and here's the point source that we extracted, and here's the residual coma. So you take that minus that equals that, right? And they all look pretty reasonable, right? So it's not like the point sources came out crazy or something, and the comas look weird, right? And you know, and so but the technique, like I said, the fundamental assumption is that what you pull out of the point source here is actually identical to the nucleus. And the good thing is that we know that the technique does work in principle, because there's been several spacecraft flyby targets where the technique was done beforehand to sort of predict what's going to happen with the size of the nucleus when the spacecraft gets there. And people got it right? So there were about 19p for 9p for 103p. People did the same kind of thing. They took pictures, images of the comet. The comet was active, but you photometrically extract the point source out of it, and you say, like, okay, that's the nucleus. And what does that say for the size, right? And we were able to get some reasonable constraints on the size of the nuclei before the spacecraft actually got there. So we know the technique does work. The question is, right, is it going to work all the time? And these were all images taken, like I said, at 4 or 5 AU from the sun. So they were, 3 or 4 or 5 AU from Earth, right? So there's a lot of stuff that could be hidden within the pixels of there. And one thing I can show you from the paper, from the SEPCON paper. This is a histogram of the ratio of the radii we got from SEPCON versus the radii that have been published elsewhere, right? So we looked at several other published surveys. This is the paper from Colin Snodgrass et al. That came out a few years ago. So this is the ratio of the Snodgrass radius to the SEPCON radius. And you think that if everybody were consistent in their answers for the radii of some of these objects, there'd be this big spike at a ratio of 1 because we all got the right answer, right? And what's funny is that the histogram here is actually kind of has some spread to it, right? And so the difference between the gray part of the histogram and the white one. So let's see, yeah. So the gray histogram only includes the nuclei in SEPCON that were bare. So they didn't actually even have to have any extraction, right? They were just bare nuclei, and we measure them, right? So these would be, if you on some level you'd think that maybe these would be the most reliable ones, but there's a big ratio here. There's some nuclei that we found that were bigger than what Snodgrass et al. Published. There's some that are smaller than what Snodgrass et al. Published. So the reason I show this, and this is something we put in the paper. So we showed that, yeah, there's something interesting going on with nucleus photometry. Okay, right. And so it means that you have to be a little bit careful about what you actually interpret in point source photometry when stuff is many AU away, because you can hide a lot of dust potentially in the point source, right? So it is possible that many comets that appear to be point sources at relatively high heliocentricity still in fact have this contamination, right? So you have to be careful. And it's not, and I should mention, right, I'm not trying to make a comment about if somebody else got the wrong answer or we got the wrong answer, right? This is just a statement about what people have published about various radii, right? And again, most of the time we look at these comets and they're very far away, and there can be a lot of stuff hidden in the since we have low spatial resolution. Okay, so I'll finish with just some open questions. Are there differences in the thermal properties of the Halley types, the Centaurs, the old long period comets, the new long period comets compared to the JFCs? Most of the stuff we've shown, most of the work that's been done is on JFCs, right? But there's all these other dynamical classes that we don't really know too much about thermally yet. And then the big question is also going to be how typical is 67P compared to anything else. That comes right back to the basic problem. You go deep on a few objects versus going shallow on lots and lots of objects. How do you know the things you're going deep on are typical? And some things that maybe will come up during discussion today. I don't know. How does cometary activity change the surface and alter the thermal properties? What is the most physically valid way to model the surface structure on a comet, on a cometary surface? How much thermal talk is there between the ices and the rock material on the surface and in the interior? And at what length scale does that crosstalk happen? These are all things that are important for understanding the basic idea behind what's going on with the thermal emission. So thank you.
Jan, very nice, nice work. Regarding to this difference between the radio computed by Snodgrass and the radio you derive.
Yeah.
This spread can't be due to an albedo difference because Snodgrass assume albedo 4%.
Yeah.
And you have some comet that the albedo determination is 2 or 6. And this produces 2% produce a difference in radio very big.
Yeah, that's absolutely true. There could be albedo differences tied up in here. Yeah, that could account for some of it. You're absolutely right. I mean, that's sort of the next thing we're working on with the survey, right? Is trying to understand the albedo distribution now to sort of fold that in and understand more of the biases.
Albedo distribution is very narrow, but very narrow. Can be 50%.
Right, right. Yeah, that's right. If it's still 2 to 6%, right, that's still a big range in terms of fractional value. Yeah.
Any other questions? I actually have a question myself, and I guess it's the one you. Well, yeah. Okay. So, I mean, you had this thought about eta being 1 and inferred thermal inertia from that.
Yeah.
That, of course, ignores roughness, right?
Yeah.
As you showed convincingly in the first few slides.
Yes.
There is significant roughness.
Yes, that's right. I readily admit that, yes. So this is basically taking the bare bones 0th order next step beyond the eta. Yeah, I totally agree. Yeah, so reconciling the broad results from a survey with the specific results from, say, Temple 1 or Hartley 2, that some work has to be done to understand that. Grissanadel put a little bit of that in their paper, but I think that has to be, there has to be some work for that.
Higher thermal inertia with roughness.
Yeah.
Nice talk, Jan. I was interested by the plot you showed at the beginning of the temperature as function of the angle. These ones.
Yeah.
So I wonder if the lower temperature compared to the subsolar point temperature that you would get from the thermal equilibrium, instantaneous equilibrium, is due to presence of ices, because then you have to include the latent sublimation and then the diffusion of this volatile species, which I get will lower the temperature.
Just depress the temperature. Yeah.
I don't think Grossan included that. Right?
Yeah, they didn't. Yeah, they didn't put it in their. They didn't put it in the math. They didn't put it in the model. Yeah, but they discuss it a little bit in the text that might be one of the things that has to be accounted for to get. And they actually had to do that. Jianyang Li actually had to do that for the analysis of Borelli, because the temperature is depressed in one end of Borelli, and if you throw in the sublimation, the energetics from sublimation, then it works out better. Yeah.
Thanks, everybody. Oh, we're sort of running short on time. Okay. Do I have time for a quick question?
It'll be a quick one. Jan, this temperature is actually the peak temperature probably, because infrared fluxes are measured, right? If you have hot spots that show that temperature, they will basically determine the total flux. Is that correct? It's not an average temperature.
Yeah, it's I guess it would be, I mean, because could you say it's an average over the resolution element?
Well, it's an average
probably
T to the power of 4 or something.
Yeah.
Like
well, okay. Yeah. I mean, they were. You know, they have thermal spectra for each point, and they were fitting the thermal spectra. There's also The paper also talks about an anisotropy factor going into the analysis to try to pull out the temperature, separate the temperature effects from the topography effects. But
so that might not be the physical temperature or the average temperature of the surface if you just average over temperatures.
Yeah.
Okay. Well, thanks a lot. I guess we have to move on. Next talk is by Mike Kelly. But thermal properties and models of comet dust.
Use your own.
I need you to leave.
Yes.
That looks okay. Okay, great. Yeah, thank you. Thanks everyone for being here, and thanks for the invitation to talk about thermal properties and models of comet dust. And now that I have your attention, let's talk about cometary science. So I started a cometary science newsletter earlier this year. It's just dedicated to, like you see, cometary science. Mostly it'll be abstracts of journal articles, but there could be other things. So cometarysciencenews.org, check it out, sign up for the emails. Okay, enough about that. So first, a little bit of science motivation for studying comet dust. Let's put this in the context of the life cycle of dust in the universe and the galaxy. So starting with interstellar medium or molecular cloud material, that is the input into solar system formation. Solar system formation transforms that material into outputs, so planets, asteroids, comets, etc. In terms of dust, that transformation happens primarily in the inner disk, maybe not exclusively, but primarily. So very close to the sun, we have sublimation and condensation. The material is destroyed and reformed as new material. Somewhere else in the disk is chondrule formation. Maybe even that's perhaps a secondary process. Still occurs and is still relevant to comets, though. And then even further out, you can have annealing can happen, of course, closer to the star, but you can have annealing by nebular shocks, even out as far as the orbit of Jupiter. Annealing being the transformation of a dust grain from its amorphous state into a crystalline state. So once you've processed that material in the inner disk, you need to transport that and mix it into the outer disk where comets are. That will be mixed with ices, with any kind of unprocessed dust that's left over, if there is any at all. So a question that's relevant to comet science is how much of that new dust mixed out in the outer disk, and how did it seed, say, the outer disk? So did it leave a radial gradient? This is, say, new dust fraction versus heliocentric distance. Was it more new dust rich in the inner part of the outer disk and then decreasing with heliocentric distance? Was there a temporal gradient? Is it that the first comets that formed have a low new dust fraction, and with time, perhaps that increased as it became more enriched? Or was that process very, very rapid and very efficient, so that we should just expect all comets to have essentially the same new dust fraction, whatever that means? So that's kind of the context of one of the reasons to study comet dust composition. Of course, there's lots of other fun things to do with them. So with that, let's talk about thermal properties and models of comet dust. What I'll do is talk about what I call the Hanner-Harker thermal model for comet dust. I'll just outline how we go about modeling this material and some results tying back to the early solar system. Then we'll talk about how do grain shape effects change the thermal emission from, in particular, magnesium-rich olivine, but of course that could be other materials. So the Hanner-Harker thermal model of comet dust. Let's see. Okay, good. First of all, let's recognize that comets are really convenient laboratories for studying dust. First, number one, they have prominent silicate emission features, and we can observe those emission features from the ground. So here is 7 to 14 microns. It's a nice 10 micron window we can observe at a ground-based telescope. This is Hale Bopp spectrum. There's not just an emission feature, but there's even substructure to it. So that's information that we want to access to understand. Second, comets are optically thin. Comet comae are optically thin. So you can essentially treat a mote of dust as an independent item and independent from the rest of the coma. And then point number 3, all grains are essentially in the same radiation environment. So compared to the heliocentric distance, the source of all the energy, the size of the coma is small. So they all see the same flux from the sun. And number 4, well, we have samples and we can study those in the lab, whether the lab is on Earth or the lab is on a spacecraft. And this is why we're in planetary science, right? And this is so in terms of composition for this dust model, our composition is based on actual dust samples or samples that we think came from comets and a long history of comet spectroscopy. So with that in mind, we have 5 compositional components. I'll try not to say mineralogy because they don't necessarily have to be minerals, but these are representative of particular minerals. So first of all, amorphous carbon. This represents essentially any carbonaceous dust, any kind of carbon-rich dust, anything that is low albedo, spectrally featureless. But it could be other spectrally featureless material. Our model will just absorb that up. That's just a reality we have to live with. Then 2 more, number 2 and number 3 is amorphous olivine and pyroxene. So amorphous just meaning it's not in a crystalline state, it's in some kind of disordered or glassy, no long-range order in these grains. We use what we call a chondritic composition, so say roughly 50-50 magnesium iron content in these silicates. Then we have crystalline olivine and pyroxene, and comets tend to have magnesium-rich compositions, not exclusively, but overwhelmingly they are magnesium-rich. So that's approximately 4ths to right for olivine and approximately nth to type for pyroxene. So just to summarize the model, once we have our composition of our isothermal grain or our dust grain, it absorbs sunlight. It is isothermal, so never mind the thermal inertia. It just warms right up and emits that energy isotropically. So just a question that's kind of on the side here. When do these small spherical grains start to behave like mini asteroids? I'm interested in that answer. Think about it. So we can talk equations at this meeting. Great. We do radiative equilibrium, assuming a spherical geometry. On 1/2, we are balancing the input from the sun. This is the cross section of the grain. This is energy coming in from the sun. Here is the absorption efficiency averaged over the sun's averaged over the solar spectrum. So this is where our grain composition comes in, and grain size. Low albedo grains will absorb more sunlight than a higher albedo grain. Then balancing that with the emission from the grain, so surface area, power given from a given temperature, and then we average over the emission efficiency for the dust given that temperature. So solving this equation for temperature, we put that into the Planck function, multiply that by the emission efficiency. Now we're doing this by wavelength rather than averaging over the entire thing. So this will give us a thermal emission spectrum, cross-section of the grain, and then distance, and that'll be our observable. So for the amorphous species, we can just use mean theory. Mean theory works really well for determining temperatures and also for giving us mid-hour emission features for the amorphous species. It's not particularly useful for the scattered component, but it works well enough just to give us the temperature. So this is a plot of absorption efficiency versus wavelength. Both are log scaled. And these are different grain sizes I've plotted. So at the bottom is a grain size of 1/10 of a micron. Then the next one's 1/2 a micron, 1 micron, 5 microns. And then at the top is for 10 micron radius. We had a question yesterday about the emissivity of particular materials, especially silicates. What happens when you go shortward of 10 microns and you see there's a precipitous drop? They become very transparent in the near infrared. So this, just to kind of tie that loose end up. Looking in particular at that 10 micron window where a lot of our comet data is, so 7 to 14 microns, Q absorption now both on a linear scale. Again, so here's a 1/10 of a micron. The feature kind of shifts a little bit shortward when we're getting up to, let's see, what, 1/2, 1 micron. 5 microns looks very different. And same thing with 10 microns. I think this is 5 and that's 10. Either way, the shape of the silicate emission feature does give you information on the grain size. Not only is temperature a part of that equation, but also the shape of that emission feature. For the crystalline silicates, mean theory does not work very well. It doesn't reproduce resonances either in the lab or in comets. So instead, what we're using is a technique called the continuous distribution of ellipsoids. You can read about that in Fabian et al. 2001. This plot is a laboratory spectrum of a powder distributed in a medium. And let's see, the other solid line, there's 2 solid lines, is the CDE technique. It also in that same medium, is stimulated in the same medium, and the alignment of the resonance features is what's important. So the 11.2, 11.3 micron feature is pretty similar. Wait, maybe I got that a little confused. But anyway, we use this and it works fairly well. Unfortunately, the ratios that work for us in order to get this alignment agreement are 10 to 1 to 1. So these are very long needles. Dimension of 10 versus 1 to 1. So that's not really realistic, especially given that we have samples of comet dust and we can look at them. We don't see this in abundance. There may be particular examples, but we do have a solution to that, and I'll come to that later. So we have our grain, we have a composition, we've balanced it with sunlight. Let's talk about comet coma grain sizes. In our model, what we use is what we call the Hanner modified power law. So on the large grain sizes, we have a power law slope, and then that peaks at a particular grain size. These all peak at 1/2 a micron. and then that drops off beyond that. We use a minimum grain size of about 1/10 of a micron, and that, again, agrees well with not just lab samples, although some of them may be a little finer. It also agrees well with light scattering technique, the more sophisticated things to describe comet dust. We can also vary the peak of the grain size, so we can put it smaller radii, greater radii. If we go to the smaller radii, it's more like just a single power law than if we go to the larger ones. The effect of that grain size distribution is to change the balance of the thermal emission spectrum. So given a nominal coma emission in the center here, if you add more small hot grains, that will increase, of course, the shorter wavelengths, the emission for the shorter wavelengths, or if you add more large grains, those would be cool, and that would add more to the longer wavelength side, tipping the emission spectrum. So that's another way we can get a handle on grain size. All right, so composition, I think I have enough time for this. So this is, again, that same figure I showed you, but now we have 3 panels. So here we have the emission feature of comet Hale Bopp in the 10 micron region, and we're showing how it decomposes into the different compositional classes here. So first of all, we have olivine that takes up a lot of the emission feature. If you add the crystalline component, so this is magnesium-rich olivine now, we can account for a lot of it, especially those narrow resonances at 11.2, about 11.1, and 10.5, or 10. And then in order to get the short wavelength side of this emission feature, add some pyroxene, and that gets most of it. What's not shown here is our carbon. This has already been ratioed with a effect of black body at this wavelength range. What's also not shown is the orthoenstatite that we model. Those are particularly transparent, have weak features, and so we don't always see them, although they were discovered in Hale Bopp. So looking at the broad SED, spectral energy distribution, this is a combined data set, the famous ISO SWS spectrum of Hale Bopp. You can see that in the orange. That's what's spanning most of the wavelengths. This also has some isophotometry, some ground-based spectra from high fogs, etc. But all this together, and then the thick black line is our thermal emission model. I mean, I wasn't involved in this, but it's the thermal emission model fit to the spectrum, and you see a nice agreement with all the spectral resonances. And olivine, a nice broad feature, gets, yeah, it fits fairly well. So what I want to talk about here is one of our primary metrics is the mass fraction of submicron silicates that are crystalline. So take just a silicate species and compare what fraction of those silicates are crystalline material. For Hale Bopp, that comes out to be fairly high fraction, 60 to almost 80%. And that was measured over a distribution of heliocentric distances. And that's where that range comes from. On the other end of the spectrum is something we've observed more recently. So this is Comet C 2012 K1 Pan stars in a paper that we've just submitted in the last few weeks. SOFIA spectrum with forecasts. And so we have the 10 micron window here. There's a bit of an emission feature from silicates. And we also have longer emission at 20 to 30, 17 to 27. This comet, so there's not a lot of bumps and wiggles from magnesium-rich olivine here. So what we, although there's a hint of a feature at 11 microns, what we come up with is a crystalline fraction of 20%. And looking at our 95% confidence limits, that goes from 10 to 50%. So this is distinctly not a Hale Bopp-like comet. And going through the literature, so this is a table that I've adapted from our submitted paper. we have a range of that crystalline fraction. So K1 pan-stars is at one end with a little bit with Temple 1. Comet Lulin, another more recent Oort cloud comet. And then on the other end is Hale Bopp again, Q4 Neat, which had a very Hale Bopp-like spectrum. V1 Neat was another Oort cloud comet. Either way, we have a wide range of this crystalline fraction. This is much more varied than what we see in typical T-Tauri disks in the review or the analysis of Olivier et al. 2011. So T-Tauri disks are more like 10 to 20% crystalline fraction. And we think we can compare these numbers directly because the techniques are very similar. We're looking at kind of the similar grains. So anyway, so we see a wide range in comet spectra. So what is that? Is that something related to their formation? Is that the composition that we're testing in the outer solar system? There may be a slight bias to the higher silicate fractions. We may have above 50%, maybe more common. Really tough to say at this point. What we can say is there's a range. More comets will tell us, is this going to be a bimodal distribution? Is this going to be a continuous distribution? We can test those kinds of things. So in a few more minutes we have, let's talk about magnesium-rich olivine. How does grain shape affect the spectra? So this is kind of a brief review of a paper by Sean Lindsay and collaborators who considered the discrete dipole approximation in order to understand how shape affects the spectrum of magnesium-rich olivine. So first, let's note that the indices of refraction of olivine are triaxial. That is, the coefficients depend on the orientation of the crystalline lattice. So one dimension's index of refraction will be different from the other two. So if you elongate one axis, you will have a different resulting spectrum. In other words, grain shape matters. This is the real index of refraction and the imaginary index of refraction. You're just seeing that they're different. I've plotted all three of them there. So with DDA, you can build whatever shape you want and try to simulate it as long as you have the supercomputer time to do that. So given several different shapes, including tetrahedra, including bricks, ellipsoids, then choosing how to align that shape with the different crystallographic axes. I didn't mean to show this one, but anyway, okay. That will then okay. You do that. You take that process and generate the simulated spectrum. So just to cut to the chase, what the results are is that they defined essentially 7 shape classes, but it's more like 3. So one is you can have a columnar shape, and all the spectrum that come from columns that is just one preferred axis in an elongated way will produce similar spectra to each other, independent of whether it's a brick or an elongated something else. Just the 3 different axes give you different, essentially 3 more subclasses for that columnar type. You can have the equant, so that's essentially no strongly preferred axis. So more like a brick or a cube. Or they can be platelets. So one axis is greatly reduced compared to the other 2. And then 3, and again, you can pick which axis you want to reduce. So they propose that given these classes, you can compare them to spectra of astrophysical sources and determine what is the most likely shape given in that source. So for Hale Bopp, they found that the resonance locations of the columns or the equant classes, most columns with preferred along the crystallographic B-axis. But anyway, these 2 classes were most similar to Hale Bopp spectrum, at least the locations of those resonances, the relative strengths, and also their shapes. And they conclude that that is an indication that Hale Bopp's magnesium-rich crystals formed as condensates in the early solar nebula. You can get similar conclusions by looking at those labs, at grain samples of IDPs and stardust. And there's a slew of references you can follow that up with. So in summary here, the takeaways are, well, comets are convenient laboratories for studying solar system silicates, where that material formed in our solar system, what those processes are in dynamical history. I just said a lot. I mean, that's like everything that we've been doing in comets for the last 30 years, but and probably for the next 30 years, but that's why we study them. We can use thermal models of dust to assess especially the crystalline silicate fraction. That's what we're most interested in, but there are other things we can consider. And we're seeing a wide range of fractions. We need more targets, understand exactly what those distributions are. Computationally intensive simulations and techniques are very, very beneficial to studying comets and other things. They can quantify grain shape effects in spectra in a way that seems to make meaningful interpretations of observations. So thank you.
Thanks a lot, Mike. Here's a question.
Okay, you talked. Does that work? Yeah. You talked a lot about silicates, but you mentioned amorphous carbon.
Mm-hmm.
I'm very curious about carbon in cometary dust.
Yeah.
And what I know is that what people call amorphous carbon is usually graphite, but in a microcrystalline sort and very perturbed crystalline structure. Is that what you assume as well? And where's the carbon here in the spectral and picture?
Yeah, there are no features in carbon to speak of. So okay, yeah, here's a good example. The spectra we get from the amorphous carbon is just smooth. It's essentially a superposition of a lot of different Planck functions. So we're not identifying any particular carbon species. We know there's lots of carbon in comets. We've seen that in the mass spectrometers, say, at Hale. But like I said earlier, this is representing a lot of different stuff. And if we use different indexes of refraction, maybe that'll change the overall balance here of what the spectrum looks like.
Just a quick curiosity. What are the estimated abundances of refractory calcium aluminum inclusion rich in comets?
Oh yeah, so those have been seen in stardust samples. You know, I can't say more than that. It's really tough to analyze abundances out of the stardust samples because there's such a small amount of material. Yeah, and well, just overall, it's a low mass of sample. But the CAIs, they're not strongly abundant. I can't say more than that. I mean, yeah, I understand. Yeah. Oh man, I would love to see that, but I don't think they're that even close to that.
Yeah. I remembered from a paper that Van Bokkehel published in Nature using infrared interferometry from the VLTI. He showed clearly that in some one or two disks, the crystalline abundance of silicates there is a radial is a strong function of the distance from the star.
Yeah.
And so I wonder if this observation you showed might indicate that Hale Bopp formed closer in the nebula compared to other comets.
Yeah,
what
right.
do you think about it?
Yeah, I should have thought about that a little bit more because you can get some indication of where it formed. Well, possibly get some information from other compositions, say the volatiles. One in particular is carbon dioxide and carbon monoxide. The relative abundances of those might tell you something about formation location. or D to H ratio. And yeah, I haven't synthesized that all together. Yeah. Yeah, okay, you're right. But for a particular comment, maybe that's you compare it to a model, and that might tell you something, a consistent picture. Yeah, sorry, I can't say more than that. Yeah.
Okay, hey, thanks again. We have to move on. Next up is by Javier Alejandro with the much more exciting thing that it sounds at face value when comets leave. We'll stay awake. Size, albedo, and beaming parameter distribution of asteroids in cometary orbits.
Okay. So we will talk about one of these comet asteroid transition objects, in particular, the asteroids in cometary orbits. Do not confuse with activated asteroids, right? Those are objects that are in typical cometary orbits. The outline of my talk is I will introduce what an ACO is. I will introduce the dynamical criteria recently published by Tancredi to select ACOs from the main belt, from the asteroid database, orbital database. I will summarize some of the known physical properties, the spectroscopic properties already published, some known albedo distribution from a paper by Fernandez et al. In 2005. And then I will present our own determination of diameter, albedo, and beamer parameter of ACOs on the Tancredi list using WISE data. It's a paper that it is in preparation. I hope I will finally submit it next week. And the analysis of this beaming albedo and beaming parameter distribution compared to the recent result on comet nuclei in Fernandez et al. 2013. The Spitzer subcom talk we already saw. And we will finally study the cumulative size distribution of ACOs. Then I present the conclusions on further work. First of all, let's concrete what I mean with an asteroid in cometary orbit. It's an object in typical cometary orbit that never showed any kind of activity. What a typical cometary orbit is the orbit of a comet we know came from the Oort cloud or the Trans-Neptunian belt, right? Not the main belt comets that are in the main belt. This is another stuff. And activity is the ejection of a significant amount of dust, but any mechanism. Why this is an important study? Because it helps us to understand the formation of cometary dust mantles and the end states of comets. And it's fundamental to determine the population of Jupiter family comets. If we have a big fraction of comets that are dormant comets, but are still comets, we need to know what the fraction is to determine the size of the population. And also, if there were not comets, what are the dynamical processes that is able to move an asteroid to a typical cometary orbit, which is an unknown procedure until now. So the main hypothesis is that this is an old Jewish design. You have the ice in yellow and the dust in red in the comet surface. Once the comet comes close to the sun and warm, it starts to sublimate ice, eject some dust deposit on the surface, and then you have a fine dust grain mantle on the surface that can isolate the ices of the interior, so the comet deactivates and became what I call a dormant comet. What about the orbits? What is the dynamical difference? Usually, the usual criteria we have been using for years to say, well, this is an asteroid in cometary orbit. Is basically basically based on the Tisserand parameter. Tisserand parameter is a constant in the three-motion restricted problem, three-body restricted problem, that it is related to the encounter velocity of the object with Jupiter. This is the Tisserand against Jupiter, and if we plot the semi-major axis against the eccentricity for an inclination 1, we can draw here the Tisserand equal 3 line, and you can see that the different populations are in different areas of this diagram, and that comets are mostly inside this Tisserand smaller than 3 region. Take into account that this is a 3-dimensional, it varies with I, so some of the objects that we saw crossing here are not really crossing this space, right? So most asteroids have Tisserand larger than 3, almost all comets, a few of them have a Tisserand slightly larger than 3.0 something, like Encke, for example, right? And it's very unlikely that an object goes from here to here unless it is in one of these resonances, and usually people just do not take into account objects that are in these resonances, Hildas, not Hildas, not Trojans. When we used to select the ACOs to observe, when we used to do these spectral surveys in the past. But we mostly look at the Tisserand, and some others, Jan uses also some criteria related to the mean orbital intersection distance, the MOID parameter. But sometimes what we consider an ACO activates. This is the case of the Don Quixote. This is a very interesting paper by Momert et al. 2014. Using Spitzer, they observed the Don Quixote at 3.6 and 4.5 microns, and extracted the PSF of a point-like source. This is a star. From the star here, they determined the PSF of a point-like source, extracted these images, and look what happens at 4.5. They have a remaining coma. Here, they attribute to CO2 emission in this band. They claim that this is a gas coma of CO2. And with some dust, of course. So sometimes these objects can have a very light activity, and it's interesting to follow them to look for this activity. Tancredi introduces some more criteria, because the problem is that the criteria we used we used it in the past to select ACOs include a lot of objects with a very stable dynamical evolution. The main characteristic of comets are that the dynamics is very unstable. They have close encounters with planets, in particular with Jupiter, in particular those in the Jupiter family, and their lifetime, the stability lifetime is very, very short, a few thousand years, right? This is some of the objects has a dynamic that is not compatible with the dynamic of comets. And so he selected, using this catalog, the orbital catalog of asteroid, using more than 500,000 asteroids in this catalog. He first analyzed the uncertainties of the orbits, the uncertainties of the Tisserand computed using this orbit, and discarded a lot of objects, as I will show. He uses a criteria the Tisserand smaller than 3.05 to include some of these Encke-like comets. He used the minimum orbital intersection distance criterion. He quit large object with large MOID, because in this case the close encounters are impossible, and some objects captured in resonance that protect from close encounter with planets. And finally, for the remaining object, he studied the dynamical evolution to see if this evolution is stable or not. Just using the first criteria, if you look at this diagram, say major axis against eccentricity, In blue, you have all the objects, and in red, overplotted in red, are those with precise orbits precise enough. Look, that the fraction of blue objects here is very large. In fact, he don't know why, but it is larger than the fraction of blue objects in the other part. So just waiting until have an accurate orbit, most of what we used to consider ACOs are not ACOs anymore. Well, he produced a list of 203 ACOs belonging to the Jupiter family group, and 56 ACOs with Halley-type orbits that are called Damocloids because of Damocles. With this criteria here, I will rapidly show some spectral studies of ACOs that we already did before Tancredi's criteria. And we published a paper in 2008, and also the Mayo and Binsel studying the Mayo and Binsel concentrate in NEAs in ACOS orbits. And we found that the large majority of objects with the Tisserand smaller than 3.02 are primitive in the CX or D complex. We have some S types that there's no way to have for an S type to be a comet, right? But our paper and the Mayo paper, from these two papers with almost 100 objects observed, only 12 survived Tancredi's list. So our sample of a spectra of ACOs in the Tancredi's list is very small up to now. But most of them have primitive spectra compatible with the spectra of comets, right? That comets spectra are mostly D and X or P type. Here an example of one of the best known ACO is 944 Hidalgo compared to 162 P Sidon Spring. Look at the near infrared spectrum is almost identical. And in our paper, we plotted the slope of all the primitive spectra we have of ACOs against this is the visible gradient, the slope against the Tisserand parameter. Found this funny relation of increasing the slope. So we go from C, P to D types, decreasing the Tisserand parameter. This is the limit for C types, C, B, D, P, and D in this case. And we concluded that there are a lot of interlopers here that are not comet because it's supposed to that the comets have gradients larger than 2. Most of them at least. Those are the spectra from our sample and the Mayo sample that survive. And if you look, that most of them in this case are D or P type and compatible with the cometary spectrum. But in any case, the sample is very small. More spectra is needed. If you go to the 3 microns, this is a paper in preparation by Campins et al. You don't find any hydration at 3 microns. Those are 3 different thermal extractions, right? But we don't have any band at 3 micron. No, so no hydration is what you expect to see in a comet surface. And when you observe this with the Spitzer, you have this big bump in this silicate plateau in the Hidalgo spectrum at 10 micron and some at larger wavelengths. And if you compare with active Hale Bopp, the kind of things that Mike has been talking in the previous talk, you can see that that here is an indication of dust in the surface. And this is a slide that Mike just borrowed me today. There's a spectra of the nuclei, bare nuclei of comets Ariane-Rigaud, Tempel 1 and Tempel 2. Look at Tempel 2. Again, this plateau of emission, you can have this, you can see this plateau here and here, even if the signal to noise is not that good, but here it's very clear. And this is the spectrum of a Trojan Hector with the same plateau. And the interpretation that given to this plateau is that we have a dust mantle of very fine silicate in a very castle structure. And I know paper by Josh in 2006, Josh and Mary 2006. Here, a comparison of the spectra of Hidalgo here with Hector. Look, they are very, very, very similar. So in the mid-infrared, it seems we're looking at the same thing that was interpreted by Bernassa et al. This is a paper by Bernassa et al. As this structure of very, very castle structure of dust, almost floating in the surface of the asteroids, observed in some primitive asteroid. This is Hector, this is Cybele, and Natalia, two papers by Licandro et al. And some laboratory simulations mixing the powders of some carbonaceous meteorites with potassium bromide, which is transparent, so it simulates this structure mixing this, and you can see that appear this plateau at 10 microns in the spectra when you have this kind of structure. So this is like a cometary dust mantle structure. This is what we asked for. And what happened with the albedos, which is the main aim of the talk. The albedo of some ACOs were studied in 2005 by Jan Fernandez. He measured the albedo of 25 ACOs, including 6 Damocloids. And he found that in this plot, this is the Tisserand parameter against the albedo. This is a zoom of this region here, right? Within the interesting region, the boundary between Tisserand 3 between comets and asteroids. These are near asteroids in pink. The ACOs are in green and comets are in red, right? You can see that all comets has very low albedo. In fact, Jan say that albedos below 0.075 is cometary-like albedos, and he found that 11 of the objects in his sample present albedo larger than the typical cometary-like. So 64% of his sample present cometary-like albedo. Those are the objects that remains in Tancredi list because only 11 of these 25 ACOs survived the Tancredi's criteria. Notice that the fraction is larger than for the spectroscopies because as a spectroscopy didn't take the MOID into account, and Jan did. There is also a recent paper by Kim et al. Using compiling diameters and albedo of some ACOs obtained using the Tisserand criteria only from different sources, but mainly the WISE data already published, albedos and diameter published, and found that 80% of them have albedo smaller than 10%, so a primitive object, but only 29 of these objects are in the Tancredi list. So we use the WISE data, but the WISE fluxes. I will pass very rapid through this because you all know. We went to the IPAC archive, retrieved the fluxes, uses the very well-known NITAM model to derive the diameter, albedo, and eta, using also the absolute magnitudes from the minor planet center. And using this WISE data, WISE fluxes, we determined the diameter, eta, and albedo of ACOs in Tancredi list, as we did in a paper by Lila Goa et al. About the B-type asteroids. I strongly recommend. So we determined the diameter and albedo for 49 of the 203 ACOs in Jupiter family comets. 32 of them also with determined eta, because we had enough data in the filters 3 and 4 at 11 and 24 microns, 20 something microns. And for this, for 16 of the 56 Damocloids with determined D and P, 13 of them with determined eta. And the main results are presented in this plot. I know Jan want to have the error bar here, but I don't want to make it too difficult to interpret. But usually the errors in albedo are 20% or even a little bit larger, right? Larger, say larger. No polarimetry. No polarimetry, Alberto. When you have a survey of polarimetry like this, let us know. So we have the teaser here and the albedo here. Here, this is the cometary albedo defined by Jan. And notice that the big dots are those objects with eta determined. So those objects we have very good wise data into filters. And the small dots are objects with only one filter, usually W3 filter, and not many data, right? So in this case, the uncertainties are larger, even because we don't determine only the fact that we don't determine the eta increase the uncertainty in the albedo, right? But look, most of these objects, 96% of the sample, is or within cometary or albedo or very close by. If you put the error bar here, you are in the limit. So it seems that Tancredi criteria do a very good job. Oh, then PowerPoint. Sorry. Okay, here is an histogram of albedo for Damocloids and Jupiter family Acos, and the distribution is very similar, and is very similar to the distribution of comets. Right here, this is in the paper of Fernandez of the Acos, and this is the distribution of comets, and here is our distribution. Most of them, I didn't include the object with very uncertain albedo in this plot, but there are only 3 that are far away here. If we restrict to the object with eta, this is the distribution, and this is the distribution of eta. That it has a mean value of 1, like the one that Jan presented for comets, but looks slightly different for Damocloids and Jupiter family comets. But it's also very similar to the mean eta of all main belt asteroids according to Maziero, that it is 1. So what's going on with the eta? Are there really difference between those population of comets in the eta value or not? So the next thing we look at is at the relation between eta and diameter, because in some cases for NIAS there are some ideas that the eta depends on the size because of the capability of accumulating dust of the larger bodies and so on. And in principle, this plot shows exactly the same. Seems to have a relation between a diameter, smaller object have larger eta. That means that they have less dust than the larger one. But if the other thing we explore is a relation with the aspect angle of the observation, based on previous paper that claim that there are a relation between the eta and the phase angle, particularly the one by Maziero et al. And here you can see the eta against alpha of our Acos, and we found this relation, which is very similar to the relation by Maziero et al. In blue. And if you apply this slope correction to the data, what happened with the relation between eta and diameter? Just disappear. So it seemed that the eta the eta dependence on an aspect angle make it disappear. And also, if remember, we have this eta distribution of Damocloids and Acos. When we correct this, we correct this because using our relation, we have this much more similar distribution. Right? I never seen this done in the literature. So I never seen anybody correcting eta for the aspect angle and study distribution. No, I think it's correct. But. So they move. Acos move like comets, smell like comets. Let's say they are comets, right? The final thing we did is to study the size distribution. We have very few objects to make this, and we have a very narrow albedo distribution. What we did is to use the absolute magnitude and use an albedo of 4% and variate it in a statistical way to produce this kind of cumulative size distribution for centaurs. Here we took from Brouwer et al. For Jupiter family comets here and Damocloids. The first thing we saw is that the distribution of Jupiter family comets and centaurs is similar. The slope is similar, but for Damocloids it's very different. One can say that this could be representative of the source of these two objects. The centaurs and Jupiter family comet came from the Trans-Neptunian belt, and the Damocloids came from the Oort cloud. Maybe it's just a matter of incompleteness, but we should mention that. But what happened when we compare the Jupiter family comet with the Acos? We have a slightly different distribution. The most interesting thing is that we have larger Acos than comets. The larger comet is about 20 kilometers in diameter, while in the case of Acos, we have many, or at least a few of them larger than 20 kilometers. But our interpretation of this is and also the difference in the slope can be interpreted as the mantling process effect. It is well known that the mantle formed very rapidly and forming very rapidly in larger objects. A few perihelion passages of a large object produce a huge dust mantle. I'm finishing. Right, and this makes that you have in the size distribution you have more large Acos than comets, and vice versa. So in conclusion, we can say that Tancredi provided a better dynamic criteria to select dormant comets, and I strongly recommend to use it. The visible and near infrared spectrum of these comets is compatible with this Acos is compatible with the comets. Hidalgo clearly have a fine grain dust mantle like comets, and it's our prototype Aco. The albedo distribution and beaming parameter distribution is compatible with comet nuclei. The cumulative size distribution is had the conclusion that I already presented recently, and that's all. Thanks.
Well, thanks a lot, Javier. What questions do we have?
Javier, can you go back one slide, please? I may have a better explanation than your last point. We have a paper last year, Bloom et al. 2014 in Icarus, where we show that large comet bodies, like 10 kilometers and above, which is exactly the size you are seeing here, become dormant automatically after so many passages, and the initial activity, but due to their hydrostatic compression internally, they die out. So they do not form a dust mantle, but the dust mantle becomes so sticky that it no longer can be released. So a large object, as it shrinks by about 1 kilometer, which is 100 passages or so.
So compacted more.
It is just gets stickier because of the earlier hydrostatic compression that the material was embedded deeper into the comet previously, which it remembers somehow. And then it becomes stickier, and then it has to die out. It can still show gas activity, however, no dust.
No dust. Oh, great. You pass me the reference, please.
I give you a reference. No? Oh, yeah.
Yes, thank you, Javier. Just one comment. You are using absolute magnitude from minor planet, right?
Yes.
So this means that you have a large error bars.
10% minimum.
Yes. So this means that when you apply your NITAM, you have also
20% minimum in albedo.
larger, I think so. So are you planning to get new absolute magnitudes to refine the final albedos that you get?
A campaign, an observational campaign of this object would improve also the absolute magnitude, which is very important to improve the albedos. Yes.
But all your albedos now are based on minor planet.
All the albedos now are based on minor planet. Okay.
Well, we have one more quick question, or is everybody eagerly waiting coffee break?
Okay, so I have an announcement. We will take the picture now. So we will use 15 minutes or more for the coffee break. We will move all the next section 15 minutes. And please meet all of us in the coffee break for the picture, right?
We also swap with Emily.
Okay, and for the afternoon, no, for the next section, we will have the last talk is not Bill. Bill?
Yeah, James.
You can give it? Okay, so no change. Perfect. Thank you.
So everybody back to 11:15.